We're going to discuss polar coordinates in section 5.1. Polar coordinates are a different way to think about coordinates that you're used to, x and y coordinates, and it has nothing to do with this polar, in case you're curious. So, what are polar coordinates? Well, what we're used to is so-called Cartesian coordinates, where they give you a value for x and a value for y, and you find those 2 points, and where these two imaginary lines meet, that's your point on a Cartesian coordinate system with x and y axes. We can think of that in a different way. We can specify this point by first of all specifying the radial distance, or the radius from the origin to this point. So that's part of it. But that really specifies a lot of points. There's a lot of points that are the same fixed radial distance or radius from the origin. So to kind of narrow it down, what we'll do is we'll also specify theta. So instead of just doing x and y, we can do r and theta. Now you might notice that instead of an equal sign, I have a triple bar. That stands for equivalent. So it's just a different way to think of this coordinate. Now the reason for introducing polar coordinates is because it does make certain things a lot simpler. And in certain circumstances, it's easier to work with polar coordinates as opposed to rectangular coordinates. But let's start by generating some relationships between these two sets of coordinates so that we can go back and forth as needed. The first one that we can start with comes from the Pythagorean Theorem. What does the Pythagorean Theorem say here? Anyone? Yeah, x squared plus y squared equals r squared. All right, so that's one relationship that we can use to go back and forth between x and y and r and theta. Of course, that means r equals the square root of x squared plus y squared. There's a couple other relationships that we can get pretty easily. Let's look at one of them. What if I took a look at the sine of theta? What would the sine of theta equal? The sine of theta would be y over r. And if I multiply both sides by r, I get r times the sine of theta equals y. And this really reflects the fact that sine of theta is associated with the vertical component of your angle. So y equals r sine theta. What do you think x is going to equal? Well, let's take a look at the cosine. What's the cosine of theta here? X over r. So what does x equal? R cosine theta. So x is r cosine theta. There's one last relationship that we'll mention here, and that is the tangent of theta. In terms of x and y, what's the tangent of theta? Y over x. And if you needed to, you could get theta to be the inverse tangent of y over x, but right now we're not going to go there. Instead, what we're going to work on is first plotting some points in polar coordinates. So some of those points are in our book. I think I might modify the first one. In fact, I made a little bit of a change to your handout. I've got 3 different polar graphs that we can use here to graph our points. And I want your feedback as to which one you think is the clearest. But let's start by understanding a few things about graphing points in polar coordinates. Your angles are going to be measured from the positive x-axis, going counterclockwise for your positive angles. It's always going to be the form r then theta. So we'll do problem 20-ish. I'm going to make that, let's see, let's make the point there 3 and 270 as opposed to 4 and 270. That way maybe it'll fit. All right, so let's graph 3 and 270. So what you're going to do when you graph these points is to, first of all, find the angle. So we'll go around here, 270 is down, and then you want to march out the appropriate radial distance. So 270 is here, and then I want to move a distance of 3. 1, 2, 3. So here's my point at 3 and 270. Let's try another one similar to this one. Yeah, I'm afraid so. Is that it? Do you want more? Yeah, press the button.
That was easy.
Okay. All right, so give that one some love. Yeah, that's it. Just graph the point. So let's graph a few more here. Let's graph problem number, let's see. We can probably squeeze in number 16 on the same graph, which gives us the point 2 and 11 pi over 6. Who remembers what 11 pi over 6 is in terms of degrees? 330. So that one should fit here pretty nice. So 2 and 11 pi over 6. So 330 is here, radial distance of 2, 1, 2. Hey, nice. Should I give it some love again? There we go. Cool. So some easy, friendly points here for us. Where it gets a little bit more interesting is when we start accounting for negative values as well. So let's take a look at problem 20 in the book. Is, at least what I'm seeing, is -3 and pi. And I guess we can use this graph one more time. We'll start by finding the angle itself. So the angle is pi. That puts us over here. And you got a radius of 3. But it's not just a radius of 3. It's a radius of -3. Right? So instead of going this way for 3, what do you think I'll need to do? Go the other way. So when you have a negative radius, it's like adding 180 degrees to your angle. So instead of going out here for 3, I'll go back here. 1, 2, 3. And that's where we'll find this point here. Let's practice another one with a negative radius. So let's do problem number 14. -2 and 5 pi over 6. And this one's going to be kind of interesting. So find your angle, 5 pi over 6, and then plot the radius of -2. What do you notice about this one? Yeah, it's kind of familiar territory, right? So 5 pi over 6 is a 150 degree angle. 2 would be here, but if you go -2, that puts you here. Same one as this one. So one of the interesting things about polar coordinates is that not every point has a unique name. In rectangular coordinates in x and y, you have just one name for your points. But in polar coordinates, you can have multiple names for your points. So, yeah. So that one fits right there. Let's keep going. Let's add a little bit more to this game. Problem number 24. Let's see. Yeah, we'll do one more with just a negative radius. So problem 24, negative 3 and 120 degrees. So I'm going to switch over to this graph now, just because I'm running out of room in the first one. Find your angle, then move your negative radius. So 120 is here. 1, 2, 3. We want to move 180 degrees opposite of that. So 1, 2. I got that right? Let's see. 1, 2, 3. Well, I've certainly decided something for myself real quick. I don't like this graph. It looked good on my computer. It doesn't look good here. So, all right. So that one here and that one there. We can start mixing things up even a little bit more. We can have a negative angle and a negative radius. So, problem like number 28. And let's go down to this one here. For that one, 28. Negative 3 and negative 3/4 pi. So I suggest that you start with finding that angle. As we find that angle, which way am I going to move to find the angle? Clockwise or counterclockwise? Clockwise, because it's a negative angle. So negative 3/4 is really negative 135 degrees. It's going to put us over here. So out here, 1, 2, 3, but we've got a negative radius. So we should be in the first quadrant. So negative 135 takes us to here. The negative puts us on the other side of the origin. 1, 2, 3. So this point here is this one here. You try one, maybe two here. Let's start with number 30, negative 3 and negative pi over 2. And then let me give you one in degrees. It's my own example. Negative 5 and negative 30 degrees. So let's see what you can come up with for those two. So the unfortunate thing for me when I do these recordings is that I don't have a pause button for reasons that I won't bore you with. So I have kind of a poor man's pause. So if you're watching this at home, you can just kind of like fast forward until you see me take away the pause thing here. Okay. Seems like a lot of you have gotten this then. Let's start out with number 30. So find the angle first, negative pi over 2. We've got a negative radius, so effectively what that's doing is it's adding 180 degrees or pi to your angle by having a negative radius. So instead of down here, we'll be up here. Distance of 3, 1, 2, 3. Up here. Good on that one? Good on these? All right. Cool. Let's try this one. Negative 5 and negative 30. So again, start out with the angle. That's going to put you at 330 degrees. Because we have a negative radius, I'll add 180. That puts me over here at 150 degrees. and a distance of 5, I think, is all the way out. 1, 2, 3, 4, 5. So that would be your point there in the second quadrant. So a different way to think of things. Now, the advantage of polar coordinates is that it makes certain equations, certain graphs really easy and interesting. And just kind of whet your appetite a little bit. Take out your graphing calculator. Does anyone know the equation for a circle? Circle, say, of radius 2 or something like that. X squared plus y squared equals 4, right? All right. Now, it's not something you can graph very easily on your graphing calculator, so kind of a bummer. You'd have to solve for y. It'd be square roots, etc. But let me show you how easy polar coordinates can make working with circles. First thing you want to do is change your mode. So hit the mode key, go all the way down to function, and across to polar. And let's press polar. So we'll make that selection. I want to make sure everyone's with me on this one. Got that one, polar. Then we're going to set our window. I want to set my window so that I have a square window. So just kind of copy my settings here. Now I'm in degrees. So these settings will work for degrees. 0 to 360. Theta step 5. Let's go from -3 to 3 on the x-axis and from -2 to 2 on the y-axis. And then finally, let's hit the y equals key. What do you notice is different about the y equals key when we get there? It's r. It's not y anymore, it's r. So let's just plug in a 2 here. R equals 2. Pretty simple equation, right? Hit the graph key whenever you're ready and take a look at what the graph is. Wow. That's pretty easy. That's a nice, friendly way to get the graph of a circle. Just r equals 2. Straight lines, circular shapes in polar coordinates are about as easy as linear shapes in rectangular coordinates. So it is pretty cool. It does have some nice things. Now, we are going to have to learn a little bit more about how you get that graph, what it represents, why it looks like that, etc. Oh, you're not getting that shape? Oh, this one? Oh, sure. Yeah, let's go back and take a quick look at that one. So -30 degrees puts you on this line, right? At -330. And then I start looking at the radius. The radius is negative. So having a negative radius means instead of marching out this way, I've got to go the other way. Effectively, it's like adding 180 degrees to your angle. So yeah, when you have a negative r, instead of moving in a positive direction out towards the angle that you're supposed to, you move in the negative direction, which is 180 degrees opposite of the angle that you're looking at. So instead of looking out towards 330, like it would in this one, because I have a negative radius, I'm going to look behind me and move out this direction. Equivalently, you could think of adding 180 to this and plotting a positive radius. So if I plot 5 and 150, 150 is out here, move in a positive direction. Still don't seem like you're convinced. Something about that's bothering you. We're going to practice some more of that as we do problems like 32 and 34. Let's just try one more example here for you. Suppose we have -4 and -240. Okay. So if I mow, tongue-tied here. If I move negative 240 degrees, that would be like a positive 120 degrees. It puts me here, right? Now, if this is a positive 4, I'd march out 1, 2, 3, 4. I'd be heading this way. But it's a negative 4. So instead of marching in front of the origin out towards this angle, I have to march the opposite direction, which would be out here. So 1, 2, 3, 4. We'll put that point there. All right.
When it's just like r is just negative, then you start at.
Yeah, I mean, one easy way to think of it is if r is negative, think of a positive r and add 180 degrees to your angle. So. Which was your example again? I didn't quite. Negative 3 and 120. So 120 would put you here. If it was 3 and 120, I'd be out here. But because it's a negative 3, what has to happen? So instead of moving out this direction for a positive 3, I'll move this direction for a negative 3. So that last one here, let me get a different color. That one would be, instead of out here, it'd be down here. Okay, Jude? This one here? Let's see here. Make sure I did everything right. So negative 240 would be the same thing as a positive 120, right? But because I had a negative radius, instead of being on this line here at negative 240, positive 120, I have to move 180 degrees opposite of that to account for the negative. So equivalently, equivalently, oh wait, did I do that right? Yeah, we're down here, right? Yes. So negative 4, or negative 240 puts us here, negative 4 would bring us down here. So that's this one. It's not quite equivalent to positive 4. Oh. Okay. You know what? This one actually didn't work too well. It's not 4 and 120. It'd be 4 and 300. That would be the equivalent there. So I guess you got to be a little bit careful in adding the 180. You'd have to add that to the positive angle, I suppose. Let's think. Yeah, because if you add it to the negative angle, then that's not going to work. So I'd stick with adding it to the positive angle. Let's try a few more that are going to ask us to think about these negative and positive angle relationships. And that will start with problem number 32. You're liking them so far? Well, let me ask you after we do problems 32 and 34 as well. So in problem 32, we're going to start with the point 4 and 3 pi over 4. So 4 and 3 pi over 4, that point is going to put us, well, I'll give you a chance to plot it. Why don't you find it first and then see if it matches what I've got. You should get a point that's in the second quadrant. But as we've seen, there's different names for these points. So Another way to specify this point is instead of using a positive angle, I could use a negative angle. So what would be the negative angle that would take me around to here, just like the positive angle would? Any takers on that one? All right, negative 225. What's negative 225 in radians? Yeah, so it's right here. So another name for this would be 4 and negative 5 pi over 4. Note here on your little sheet, you've got the angles and in radians and degrees. So yeah, you can take a quick look. 225 is 5 pi over 4. So those would be equivalent angles, or equivalent points, I should say. Let's try part B. Part B says I want a negative radius, but a positive angle. Well, if I have a negative radius, I got no choice. There has to be a negative 4. Now you got to kind of think a little bit backwards. Remember what the negative radius does. You know, if you had a positive radius, and then take a look at that negative, it's going to move you to the other side. So what we have to do is we have to start out on this side here, and then move over to that side. So we need the angle that puts us here. What is that angle in radians? Thank you, 7 pi over 4. So we go around to 7 pi over 4, 1, 2, 3, 4. Oh, but wait a minute, we got a negative radius, so that puts us back here. Sure. So, if I want to land here, when it's all said and done, then with a negative radius, my angle has to put me out here. So that when I get here and I account for the negative, accounting for the negative means just effectively moving 180 degrees or an angle of pi. You're moving directly through the origin. You're reflecting through here. So my angle had to put me here so that when I account for the negative radius, I end up here. So that angle was 7 pi over 4. And negative radius, you have no choice. It's going to be negative 4. Okay. Last but not least, part C. This time I want a positive radius, but my angle is going to be between 2 pi and 4 pi. So what's that mean that our angle is between 2 pi and 4 pi? Really, it means you go more than once around the circle before you get to your angle, right? So you have to figure out, well, okay, you know, that's my angle, but I need to go once more around the circle before I stop there. So how could I find that angle? Okay, 360 would work in degrees, 2 pi in radians. So you're going to take your angle, 3 pi over 4, and add 2 pi. Now for my convenience, instead of writing 2 pi, I'm going to write 8 pi over 4. Why do I do that? Yeah, you got common denominators, right? So you can see that the angle is going to be 11 pi over 4. And your final answer here should be 4 and 11 pi over 4. You can, if you're just like, oh, I hate working in radians, you can do it in degrees and then convert your final answer. So you'd start out with 135, add 360, you get 495, and then convert it to degrees, or convert it to radians, and you get your answer. So parts A, B, and C. Say again? This way or? Yep, that's perfect. I just Okay, sure. I think I have extra paper like this online, so when you're doing these types of problems, you can just print off, a few copies for yourself, make it easier. And certainly on the exams, I'll have these things written for you, so the answer is, at least as far as I'm concerned, you don't have to draw your own circles. That's kind of a pain. I want you to try one just like this. So the same 3 requirements, just going to give you a different point. Let's see, what's the point in 34? It's negative 3 and 4 pi. So problem 34. So negative 3 and 4 pi. Should be interesting. What I would suggest you do is you first plot that point, figure out where that point is, and then go from there. But we want to find a point that matches the same 3 conditions that we did over here. Part A, r is greater than 0, and the angle is between negative 2 pi and 0. And let me be very careful about where the less than or equal to sign goes. It goes with the negative 2 pi. Part B, we wanted r less than 0, theta between 0 and 2 pi. Again, I got to be careful with the less than or equal to. Less than or equal to goes with the 0. Last but not least, part C, I want an angle between 2 pi and 4 pi, and r is greater than 0. pi is less than theta is less than 4 pi. Flush. Let's see. So first one will have a positive radius, so that would make that a 3. No choice about that. Oh yes, because we don't want a negative radius, we want a positive radius. So it has to be a 3. And then if we want to do a negative angle, what's the negative angle that takes you from here to here? Yes, negative pi. So it's a 3 negative pi. Negative 3, but a positive angle. What's wrong? Because pi would take you here, negative 3 would take you over here.
Oh.
So part B is negative 3. Well, no, because they want an angle that's between 0 and 2 pi. Well, no, because it's 0 and less than 2 pi. So 2 pi would work, but 2 pi is not the sphere's problem because it's less than 2 pi. So you have to think a little bit farther. So negative 3 is where you want to start out. That's good. We want a negative radius. This time we want an angle between 0 and 2 pi. So if we want a negative radius, that means our angle has to put us over here. And then we'll do a negative radius. So what angle in this range is going to put us on speed? There's only one choice. 2 pi is not really a choice. It's less than 2 pi. So there's one other choice. Not for B, because B asks you for an angle between 0 and 2 pi. So it has to be positive or 0. Okay, so let's go through these. For the first one, for A, we want a positive radius and a negative angle. Now that negative angle, instead of getting to our point this way, in this direction, we have to go this direction. This angle in radians, halfway around the circle, is what? Pi. So if I want a positive radius, that radius has to be 3. And the negative angle would be negative 180, or better yet, negative pi, to satisfy this part. So there's part A. For part B, note that you need a negative radius. So it means negative 3 here. Now if I have a negative radius, my angle should put me here. So then when I deal with the negative radius, I end up over here. So look at your choices. What angle puts you right on this x-axis amongst all these different angles? There's only one choice. What's that? 0. Now, 2 pi is tempting, but 2 pi is not one of your choices, is it? No, 2 pi is not a choice, so the only other choice then is 0. So negative 3 and 0. Good on A and B? Last one, part C. This time we want a positive radius, so no choice there. The radius has to be 3. And an angle between 2 pi and 4 pi. So, well, it means I'm going to have to go more than once around. So I'll go pi, and then another pi, and then another pi. Effectively, I've gone 3 pi to get to that point. But you have to go once around, which is 2 pi, and then another part, which is pi. 2 pi and pi gives you 3 pi. So that's the last one in here. Okay. Any questions on that one before we move on? All right. Not hitting the easy button on that one, that's for sure. Okay. One of the things you're going to be asked to do quite often is convert back and forth between radians and, excuse me, not radians, but polar coordinates and rectangular coordinates. Problems like number 44. You've got the point 5 and 300 degrees. We want to know, well, what's that point in x and y coordinates? Well, there's a couple ways you can do this. You could draw some triangles. You could set up some right triangle trigonometry. But I think the easiest way to do it is this. X equals r cosine theta and y equals r sine theta. And we've got everything we need. Here's your r. Here's your theta. So, okay. 5 times the cosine of 300 degrees. Does anyone remember the cosine of 300 degrees? Positive 1/2. So 5 over 2. Now, if you're looking at that and going, oh, man, sine, cosine, 300, 330, I always mess those up. Look, there's nothing wrong with taking out your calculator and saying, okay, sine of 300. Now, you may not get the nice expression that we can put here with radicals, but maybe you remember something I suggested you know at the beginning of the course, and that is the decimal value of some of these expressions, like the square root of 3 over 2 is 0.866. Okay? So what that's telling you is that this is negative square root of 3 over 2, or negative 5 square root of 3 over 2 for your y coordinate. Equivalently, in x and y, this is going to be 5/2 and negative 5 square root of 3 over 2. Doesn't matter what. Yeah, you'd have to be in degrees if you want your calculator to give you these numbers. Yes, it would matter. If you're in polar mode or not doesn't matter. Polar mode is only going to really affect your graph. One other thing that it will affect, if you're used to storing things, if you use the store key, say like 5 store x, when you go to store x, instead of an x, you get a theta. And that's because you're in polar mode. And if you're like, you don't like that, you want your x back, then go to your regular function mode. So you go back down to function. And now when you do that, when you store something, it's back in x. So yeah, that's the only change you're going to see on that. Problem 48, negative 3 and negative 3 pi over 4. So again, you've got something in r and theta. And we want to find the x and y coordinates. X is r cosine of theta. Y is r sine of theta. Hate Windows. It'll probably be on the video too. All right. So we get negative 3 times the cosine of negative 3 pi over 4. Let me just remind you of your even odd identities here. Cosine is an even function, so I don't have to worry about the negative here. It's just negative 3 times the cosine of 3 pi over 4, which is negative 3 times the square root of 2 over 2. How about sine? Exactly. Thank you. So in this case, sine is an odd function, so that negative factors out. And I'll get a negative times a negative. That'll just make that a positive. 3 times the sine of 3 pi over 4, which will be positive 3 square root of 2 over 2. Hopefully you're really familiar with, let's see, wait, 3 pi, yeah, it would be positive, yeah. Hopefully you're familiar with sines and cosines at these angles that are multiples of 45 degrees. It's always going to be root 2 over 2. It's going to be a plus or minus in there, but our final answer is negative 3 square roots of 2 over 2 and 3 square roots of 2 over 2. So x and y. Yes. Yeah. One last one like this. Problem number 50. We'll do 50 two different ways. Problem number 50 is negative 3 and negative 90 degrees. We can do that kind of a brute force approach. So x is our cosine theta, y is our sine theta. So negative 3 cosine of negative 90 degrees. And then negative 3 times the sine of negative 90. What's a cosine of 90 or negative 90? 0. And the sine, it's an odd function, so that's 3 times the sine of 90. What's the sine of 90? 1. So 0 and 3 would be the equivalent in x and y. 0 and 3. This one you could have also done reasonably easily if you took a geometric approach. The geometric approach would just be to see, all right, well, where would that be graphed? So let's do it this way. Let's draw ourselves a quick little graph. So 1, 2, and 3. 1, 2, and 3. So if I wanted to graph the point negative 3, negative 90, I would start out by finding that angle. So that's your negative 90. And a radius of 3 would put me down here. But I've got a radius of positive or of negative 3, so I have to go to the other side of the origin. So reflecting it up here puts me right here. And that point is right on the y-axis. 0, 3. So it's nice that geometrically this makes sense. It matches what we would expect. Okay. Are we all right with problem 50 here? I think we'll take a break here and we'll come back and finish this up and move into section 5.2.